Okay, we are on to U2A4. This is the last activity or section of Unit 2, and what we're looking at is a very important theory called the valence shell electron pair repulsion theory, also called VSEPR. This was brought about by Gillespie. He was a researcher at McMaster University in Hamilton, Ontario. He did a lot of this work when he was still in England working, but he brought this work over to Canada. I'm going to show you how I come up with VSEPR shapes, and then you can do what you want to do. You can take a look at the content. I make this into a mathematical model. I have four columns: octet, valence, bonding electrons, non-bonding electrons. So every element gets an octet number of 8, except for hydrogen, which gets an octet number of 2. So that would be 8 plus 2 plus 2. Once again, octet means to have 8 or to have a full shell. Hydrogen's the only exception on the periodic table. Its full shell number is 2. So if you add those numbers up, you get 12. I'm going to do 4 examples of this if you miss anything. Valence is the column you're in. So, column 1, 2, 3, 4, 5, 6, and 7. So hydrogen's in column 1. We've got 2 of those in column 1. Plus we have oxygen, which is in column 6. That's 8. You will always be working with even numbers. If you work with odd numbers, you've made a mistake. Bonding electrons is your octet column. Subtract your valence column. 12 subtract 8 is 4. It takes 2 electrons to make a bond, so these are bonding electrons. So since you have 4 and it takes 2, you divide by 2 to get 2 bonds. Non-bonding electrons, what you do is you subtract these 2 columns. So you always go back 2 columns and subtract. 8 minus 4 is 4 non-bonding electrons. Okay, so to get this column, you subtract these 2. To get this column, you subtract these 2. So what do we have? We have H2O. Write down the one you have the least of in the middle. That's O. You've got 2 H's. This says you have 2 bonds. There's a bond, there's a bond. A bond is made up of 2 electrons. Now, I always cut my bonds in half to show where the electron belongs. This belongs to this element, this belongs to this element. I've got 4 non-bonding electrons. How many electrons is hydrogen supposed to have around it? It's in the first column, so it needs 1. Oxygen is in the 6th column. It's only got 2 electrons. Because it's in the 6th column, because it is in the 6th column over, it needs to have 6 electrons. Where are those going to come from? The 4 non-bonding electrons. They always come in pairs. It doesn't matter where you put them, but we'll put them right there. When I say it doesn't matter where you put them, they've got to be with the oxygen. But you need to have 6 electrons with the oxygen. 1, 2, 3, 4, 5, 6. Now we're going to do something called AXE designation. There's one central atom, oxygen. That's the A. There are 2 side atoms. That's the X, AX2. The E is the number of pairs of non-bonding electrons on the central atom only. So we're only looking at these pairs that are on the oxygen. There are 2 pairs. The most common mistake is for people to say, well, there's 4. No, there's 2 pairs. AX2E2. So if you do what I've just done and you look up AX2E2, you will find a shape given that. So when you go on and you go through this unit, there will be a shape sheet. All you do is look up AX2E2 and let's say that it is bent. Then you just write down bent for your final answer. Let's do OF2. I said we would do 4 of these. This is all repetition. I said every element gets an 8. 8 8, and 8 is 24. Oxygen's in the 6th column, fluorine's in the 7th. 7, 7, 6 is 20. Let's take a look at that. Oxygen is in the 6th column, fluorine is in the 7. Subtract those two. 24 minus 20 is 4. You got 4 bonding electrons. That's 2 bonds. And 20 minus 4 is 16 non-bonding electrons. Put the one you have the least of in the middle. Take care of your bonds. I split my bond in half, and it's made up of 2 electrons, one from each element. Remember what I said, fluorine needed 7. It's in the 7th column, it needs 7 electrons. So that's 3 pairs of non-bonding electrons. I've used up 12 of these now. I have 4 left, so that's 2 pairs there. What is this? It is A, X2, E1, 2. You don't count the non-bonding electrons on the fluorine. So then you would look up AX2E2 on the chart that's in your content, and it would tell you what the shape of the molecule is. NH41 plus will throw a wrinkle in here. Octet. Every element is 8 except for hydrogen, which is 2. 8, 2, 2, 2, and 2 is 16. Valence, nitrogen's in the 5th column, hydrogen's in the 1st. 5, 1, 1, 1, and 1 is 9. Whoa, whoa, whoa. I said we couldn't use odd numbers here. Notice this has a 1 plus charge. That means that we have 1 less electron. So if you have a positive charge, you take electrons away. If we had a negative charge, we would add electrons. So we take care of that in this column right here. 16 minus 8 is 8 bonding electrons. That's 4 bonds. 8 minus 8 is 0 non-bonding electrons. Put the nitrogen in the middle. Put the hydrogens around it. Break up your bonds. That's A, X4, 1, 2, 3, 4. The A is that single one in the middle. There are no E's here, okay? So there are no non-bonding electron pairs on the nitrogen, so it's just AX4. The shape will be, if you look up the shape of AX4, it will say tetrahedral. NH3. Eight, 2, 2, and 2, that's 14. 5, 1, 1, and 1, that's 8. 14 minus 8 is 6, that's 3 bonds, 2 non-bonding electrons. So I'm going to talk about what Gillespie actually said when I draw this one. I'm going to write N, H, H, H. Remember what I said about the N. It's in the 5th column, therefore it needs 5 electrons around it. 1, 2, 3 in bonds, and then 2. Each hydrogen needs 1 electron. Okay, here's what Gillespie said. He said electron pairs in bonds will push each other apart so that they can maximize their distance apart. If we did CH4, this triangle means the bond is coming out towards you. This dashed line means it's going away. Each one of these bonds would have an angle of 109.5 degrees. Because this is in 3 dimensions, it's not flat. You might think it would be 90, 90, 90, and 90. But because it's in 3 dimensions, it's 109.5 degrees. So what Gillespie said was we can find the shape of molecules because each of these will maximize their distance. Now, here's another interesting thing that Gillespie said. When you have non-bonding electron pairs, they have a greater repulsive effect. So they push these guys even further apart. Okay, so he said bonding pairs of electrons, whether they're double or single bonds, will have the same effect to push the bonds apart. And if you have non-bonding pairs, they push them apart even further. This is very important in a lot of number of areas of chemistry. And I'll just give you one simple area where this is important. If you make artificial sweeteners, they have to fit into your taste buds in exactly the right way. So you need to have things that are exactly the right distance apart to get things to fit. That's just one small example as to where this is important. Folks, this is how I teach shapes. If the content makes more sense to you, go with it.